Okay, so today we're going to be moving on to assignment number 6. And assignment number 6 is about the multiplication rule of independence. And so this is something that we're going to be focusing actually on this lesson, and then a couple more lessons after this as well. So it's kind of a building block for what is to come. So let's go ahead and get started. So in this lesson, we're going to get into multiplying two events together with A and B. But real quickly to review, the probability of not A is always 1 minus the probability of A. If I have A or B, well, then I add the two probabilities together. That works for mutually exclusive events, but if for not mutually exclusive events, but if the events are not mutually exclusive, then I have to subtract the intersection. So that should be not mutually exclusive. That should be not mutually exclusive. And then the probability of B given A, the given part is always in the denominator, and then this is both of them. And then today we're going to get on to the probability of A and B. So that's going to look like this. It's going to be a foundation part to remember this as well. The probability of B given A is the probability of A and B over the probability of A. That's what we talked about in lesson 5. So here we have the general multiplication rule. So if we have two events and we want to know the probability of both of them happening at the same time, we're going to take the probability of A and the probability of B given A and multiply those two events together. Let's get a better idea of what we're talking about here. So in the 113th Congress of the United States, there were 18.7% were senators. The other were representatives, but 18.7% of them were senators. And of those senators, 53% of those senators were Democrats. Okay, so we want to know what's the probability that a congressman chosen at random is both a senator and a Democrat. And so here's our equation that we're going to be using. The probability that they are a senator first is going to be 0.187. And then the probability that they are a Democrat, given that they're a senator, that's this right here. So 53% of the senators, that's the denominator. That means it's a conditional probability because we're only talking about the senators, is 53%. So I would take 0.18, get my calculator here. I would take 0.187 and multiply that times 0.53. And what I would get is 0.0991, which means that roughly, really close to 10% of all congressmen are going to be senators who are also Democrats. Let's tell you how this looks like in a more concrete example. So we have male and female frequencies in Mr. Panning's Honors Algebra 2 classes below. So we have 40 students altogether, and of those 40 students, 17 are male and 23 are female. And so we want to assume that two students that came to Mr. Panning wanted to drop his class, let's say. We want to know event F1 would be that the first student that wanted to drop his class was a female, and M2 would be that the second person was a male. So what's the probability of both of those happening at the same time? Well, if we use the formula here, we're going to first find the probability of F1. Okay, the probability that the first one was a female, and there are 23 females out of 40. So the probability that the first one was a female is 23 out of 40. And then we're going to multiply that by the conditional probability of the second one, which is the probability that the second student was a male. Well, we have 17 males in the group, and if the first one had already dropped, that means we only have 39 students left. And so the conditional probability of M2 given F1 would be 17 out of 39. And so then we're going to go ahead and multiply those together to figure out what the total probability would be, I can take 23 times 17, which is 391, and then divide that by 40 times 39, which is 1,560. And if I divide those two things, 391 divided by 1,560, we get 0.25. So really close to 0.25. So about 25% of the time, I would have the first student would be a female and the second student would be a male. And you can see this diagram kind of helps us figure out what those probabilities are. Remember the first probability, the probability that the first student was a female was 23 out of 40. Given that that happened, now we only have 39 students left, so the probability that the second student was a male is only 17 out of 39. And we just multiply those two probabilities together to get the close to 25%. So here are the things we should know right now. From a couple of times ago, if it's the probability of not A is going to be 1 minus the probability of A. If two things are mutually exclusive, then we can say the probability of A or B is simply the probability of A plus the probability of B. If they are not mutually exclusive, then the probability, we would have to take the probability of A plus the probability of B and subtract the intersection of those two probabilities. If it's a conditional probability, then what's given is in the denominator, and then the numerator is the probability of both of those events happening at the same time. And now we have the probability of A and B. And the probability of A and B is going to be the probability of A times the probability of B given A. There's one more rule that we want to talk about, and that is a rule of independent events. And so what is an independent event exactly? So event B is said to be independent of event A as long as if one of those events occurs does not affect the probability of the other event occurring. So an example would be, let's say event A is that you pick a card from a deck of cards and you get a heart, okay? Well, we know that there are 1 out of every 4 card is a heart, okay? The probability of event B would be that you draw a card and the card is a face card. Well, we know that there are 12 face cards out of 52, and 12 out of 52 reduces to, let's say, 6 out of 26, which is 3 out of 13. And so let's say that we draw a heart first, okay? We did that first, and then we drew another card and we got a face card. Well, the probability wouldn't change. Or if I picked a card and I drew a heart, or I took out all the hearts and I drew a face card from the hearts, the probability would not change. These probabilities don't affect each other. So they are called independent events. So if we have let's first look at another situation. Let's say that we have 3 different events. The first event is that a face card is selected. Okay, that's what event F would be. Then the second event would be that a king is selected. That's the event K. And then H is that a heart is selected. Well, is K independent of F? Well, suppose we know that F has happened. We've selected a face card. Okay, so what we have is we know we have a face card in our hands. So what's the probability that that face card is a king? Well, there are 4 kings out of 12 face cards. That's different than just selecting a king by itself, because that probability is 4 out of 52. These probabilities are different, which means that this is not independent of each other. Where the example that we just talked about before is the events K and H. If I do H first, the probability that a heart is selected, okay, so I know I have a heart. So if I have a heart in my hand, what's the probability that it's a king? Well, there's one king out of 12 hearts, or out of 13 hearts. So the probability is 1 out of 13. Well, if I didn't know that heart was selected and I just did a king first, well, there are 4 kings out of 52 cards. These are the same probabilities. So that makes it an independent event. And if we have independent events, then the equation is much simpler. The probability of A and B can be found just by multiplying the probability of A times the probability of B. So an example of this would be Suppose we want to find the probability that a dice is rolled and a coin is flipped, and we want a 1 and a heads. Well, the probability of rolling a 1 is 1 out of 6, and the probability of rolling a heads is 1 out of 2. So what's the probability of both of those happening? Well, that's going to be 1 out of 12 because we simply just multiply those together. And that's what this formula is saying. So if we had a review of all of these things, again, this should be mutually exclusive here. We have all the probabilities that we've talked about so far, the negation rule, the rule for OR, okay, which is really just one rule. We always just add the two probabilities together, and if there is an intersection, we subtract them. Conditional probability rule, which is this one, the A is always in the denominator. And then we have the two rules for A and B happening. And that would be, we either multiply A times B, the probability of A times the probability of B if they're independent events. But if they're dependent of each other, we take the probability of A times the probability of B given A. And that's what our rules are for assignment number 6, and that's what our homework assignment is about. There is an extension to the multiplication rule, and that is if I have more than 2 events, like the probability of A and B and C happening, well, I just multiply all those individual probabilities together. Okay? An example of this would be, let's say you go and you're playing roulette. On the roulette wheel, there are 18 red numbers, and there are 18 black numbers, and there are 2 green numbers. So you would bet on either having a red number show up or a black number show up, and if a green number shows up, then everybody loses and the house takes all the money. So we want to find the probability of first getting a green number, then a black number, and then another black number. Well, these are independent of each other. The probability of rolling a green number first is going to be 2 out of 38. 18 plus 18 plus 2 is 38 total. Then I want to know the probability of getting a black number. Well, that's going to be 18 out of 38. And then the probability of getting another black number, well, there's still 18 out of 38. One doesn't affect the other, and I'm just going to multiply those together. And that's going to give me the probability of getting a green one, then a black one, and then a black one. So remember, independent events are not mutually exclusive. They can happen at the same time. It just means that the occurrence of one does not affect the probability of the other. And that's what assignment number 6 is about. That's what our homework is about today. And that'll be in Math Excel. And work hard on that, and we'll go over those questions tomorrow in class. Good luck, everybody.